Welcome and thank you for joining us. My name is Dean Lee and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today we have the great pleasure of presenting a public lecture by Professor Philip Kim entitled Physics in Flatland, Searching for New Quantum Materials for Emerging Technologies. Professor Kim received his bachelor's degree in physics at Seoul National University and received his PhD in applied physics from Harvard University. He was a Miller postdoctoral fellow in physics from University of California, Berkeley, and then he joined the Department of Physics at Columbia University as a faculty member. But since 2014, he has held a post at Harvard University where he is a professor of physics and applied physics. The focus of his research is the mesoscopic investigation of transport phenomena, particularly electric, thermal, and thermoelectrical properties of low-dimensional nanoscale materials. These materials include carbon nanotubes, organic and inorganic nanowires, two-dimensional mesoscopic single crystals, and single organic molecules. Professor Kim has also received numerous honors and awards, including the Benjamin Franklin Medal in Physics, the Tomasoni Chesesi Prize, the Oliver E. Buckley Prize of the American Physical Society, the Dresden Barkhausen Award, and the Hohem Science Prize. And he is an elected member of the National Academy, the National Science Academy of Science, and the American Academy of Arts and Science. If you have any questions during this talk, please type them into the chat or question and answer dialog box. At this time, it is my great pleasure to introduce Professor Kim.
Thank you, Professor Dean Lee. It is my great pleasure and honor to be invited to deliver this public lecture. I know that Sunday afternoon there are many things that you can do, and I'm glad that the many of you just come for just to listen some of the piece of the physics that I want to kind of share. I try to kind of give the talk a little bit more entertainable. I try my best to make the kind of your Sunday afternoon enjoyable. So as a kind of this topic, the title slide said, I will just talk about some things about the quantum materials and then applications based on that. But this the particular quantum material that I'm going to talk about is so-called the flatland. And you may ask, what is the meaning of the flatland? And that's probably the first slide I want to kind of deliver. Okay. Okay. So, in fact, the Flatland is something that I borrowed the title of the novel that written in sometimes at end of the 19th century. That the novel written by the Edwin Abbott, and this Edwin Abbott was just kind of describing interesting. In the modern world, it could be science fictions. Think about the hypothesis that if somebody live in the two-dimensional space, that the one of these the main character is a square, and he goes through a lot of adventures throughout this novel, and especially his first encounter of this higher dimension object like the sphere in the 3D. I think will kind of give him a lot of trouble there. This novel is quite interesting. I think maybe it's a good time of the passing time the reading. But also it turns out that there's a movie based on that. It was 2007 that there's a Flatland movie comes around, and it was kind of quite accessible movie, and it's enjoyable. So you can just take a look. There's a YouTube link that I can just put up there. I think this is kind of good example that mathematically we can envision that the 2-dimension, 1-dimension, or 4 dimensions, and all this kind of different dimensionality is always kind of fascinating topic to discuss. However, it's more of the mathematics. But when we say the flat land, the physics or the 2 dimensions, so 1-dimensional object, it's hardly imagine that it can exist in the physical world, because in some sense, the tiniest the object we can think about, atoms, electrons, or some of these things, we always think about, well, has some kind of the length scale that it just exists in the space, in the three-dimensional space. So most of the object, including materials, think about the flat materials, the low-dimensional materials. It cannot just kind of get into this mathematical abstract concept easily, right? So to understand that when you say the flat material, that material is a two-dimension, therefore that we need some of the other way of the thinking about this subject. And that basically brings us that importance of the quantum mechanics. So let me wind the clock. It's about 100 years ago. About 100 years ago, that it was a really exciting time. The physicists in the world, part of the reason is that's a time that the special relativities and general relativity start kind of established in firm ground. And the quantum mechanics is kind of almost established kind of about the time. And this is kind of one of the famous photographs of one of the conference pictures taken around that time. There are a lot of these important people in this among these scientists. Albert Einstein is there. For example, Madame Curie is here. And a lot of this giant of this physics at the time gather together, make this conference. And this is about the time also that Erwin Schrödinger wrote his famous Schrödinger equations that describe, that provide some basic understanding of basic tool sets for the quantum physics that born around this time. Now, this quantum physics actually provides us a new window to look at the nature. For example, that classically, that when we look at the hydrogen atom, which consists of the electron and proton, and that one way we can just theorize those kind of hydrogen atom is because there's attractive interaction between the electron and proton. We want kind of make that this electron doesn't fall onto the proton by making some of these orbits. So very classically, like this planet orbits, one can think about electrons circulating around the proton, and that make the stable orbits. And that's kind of one way we can understand this hydrogen atom in classical view. Of course, even classical physics, this doesn't work too well, because charged particle, when you start to accelerate it, like the circular motion, start to emit the light, and the orbit cannot be stable into this two charged object in classical point of view. And there comes quantum mechanics save us, that by solving this so-called Schrödinger equation I just mentioned, turns out the modern view or quantum view of the hydrogen atom can be very different from classical view. And as I'm showing here, that there are various different orbits of the electron around the proton, following through the solution of the Schrödinger equations. It looks complicated, but there's one important aspect that compare with this classical to the quantum. There's one big difference, and the big difference is where in the quantum, unlike the classical, that all this orbit is rather discrete, meaning that there is a certain orbits. Of course, the orbit itself is continuous, but one orbit to the another orbits, there is only kind of discrete, the states kind of exist. And this discreteness is a kind of something that really distinguishes between classical and quantum. And that's basically one important kind of point of view we can take on. In fact, this discreteness comes from so-called the concept of the quantum confinement. The one nice nature of this Schrödinger equation is if you just solve these equations to describe the certain quantum states, when this state is confined in the space, such as the hydrogen atom, for example, the electron is basically kind of confined by the attractive interaction of heavy proton. So it's always around this proton. And that's basically an essential part that why we get this discreteness of state, and related with the discreteness of the energy state, you can just kind of plot it out. Let's imagine that now I have this small object that I can describe the discrete quantum state. And I simply just extend this object in one of the directions and make this, rather than small ball, I make the y out of it, right? And then along this, the perpendicular direction, the axial direction of the wire, things are still confined. But along the y direction, if this stretch the y is longer and longer, there's no confinement. Again, that solutions of the Schrödinger equation of quantum mechanical description tells us that that there's a discreteness comes from the x and y direction, or the perpendicular to the axial direction. but there is no discreteness along the axial direction. Things becomes a little bit more continuous, but that contains a discrete natures in there. Now let's stretch these wires another direction and turn that into pizza box. And this kind of flat boxes, that still the confinement exists in the vertical direction of the flat the surface, but other direction is kind of free. So that the discreteness of this energy state becomes a little bit more continuous, but you can still kind of see that vestige of the discreteness by counting the steps. Especially when you get into the lower step, the quantum states, basically that frees out all these kind of vertical motions, effectively describe the system into this 2-dimension, right? So compare with this kind of bulk where there is no the confinement. Therefore, that if I just kind of reduce the dimension of the system small enough such that this energy scale we get involved is larger than any of the characteristic energy scale, such as temperature or something that you just excited system, excited energies. System effectively behave like the low-dimensional system, such as 2D and 1D, even we can call it the 0D, if it is kind of really confined into the very small space. And that's basically how we can understand the effectively low-dimensional system using the quantum mechanics. Right. I guarantee you that this is close to kind of last equation I'm just going to show you today. But you will see that, all right, maybe you can guess that, okay, so now I can maybe just pretend to understand how the low dimensionality works in the quantum mechanics. Is this really kind of related with something that we really do care about? I would say that yes, it does. If you just look at the me through the computer screens or the iPad or whatever, that we normally rely on this modern electronic technologies, and basically that's based on that so-called computer chips. What's in this computer chips? If you just open up the computer chip and look at inside, of course, it's made of silicon and the metal connection. But if you zoom in and into the basic part of this complicated circuit, the basis of the circuit is what you call the transistor. And transistor is nothing but just electronically working switches. But if you just look at this kind of zoom in the switches, now I think the engineers, electrical engineers make the transistor so small. And the basic part of the switches that now encompass only a few atomic length scale of this channel dielectric. So to enable all the electronic technologies, now engineers at least can deal with even a few atomic length scale of these materials down to this kind of confined space. Therefore, that without quantum mechanics, understanding and engineering this type of this object is kind of virtually impossible. So it is deeply related our technologies. Engineers went through this a lot of the progress over the past probably several tens of years. And then the techniques has been developed now that one can create these materials really atomic length, atomic layer by layer. And this is what we call the so-called molecular beam epitaxial techniques. And grow this material by layer by evaporating that certain atoms by layer. And as a result, if you just kind of make the cut of this grown substrate, and if you just take the look at how those the material look like, you see that there's this white the line that's basically a cross cut of this wafer, and each of the white cut consists of one atomic layer. And now we can just grow this atomic layer by kind of different constituent of atoms and give you some of this kind of functionalities on all grown materials. And this type of the technology is now being widely used, not only to try to study the physics, but also practically being used in many of our electronics, including our computer chips, our LED lights, and all of these things based on the techniques that we can grow these materials at really atomic scale, right? Another interesting the variation of getting this atomic layer, by the way, even in your kitchen, is something like this. There's a material called the graphene. In fact, this graphene is material that I've been working on past 20 years. This is one single atomic layer of the carbon that basically the carbon atom arranged the chicken net type of hexagons and make this nice network of the atoms. It turns out the graphene is the thinnest material you can get. and truly two-dimensional materials in that regard. And it displays a lot of these interesting physical properties into these materials. It was discovered only in 2004, about 20 years ago, by just this duo, the Andre Geim and Kostya Novoselov, and within 6 years, the scientist actually got the Nobel Prize by just kind of this achievement of discovering this the unique form of the materials. While this material shows a lot of exciting properties, getting these materials, by the way, that how these two Nobel duo got this material is deceptively simple. And I can show you how it worked it out. In fact, you can just get this one even in your kitchen. It works in the following way. So let's starting from the graphite crystal. You can get it the various way, or you can even just kind of pencil lead contains a decent amount of graphite crystal, graphite. So you can use even that. You just kind of get the graphite crystal and piece of the Scotch tape. You just kind of wet this graphite crystal onto a piece of Scotch tape, and you fold the Scotch tape a couple of times, right? And then this the flaky material can be easily cleaved down to the many different pieces here, right? And just bring down Scotch tape with a piece onto the flat surface. Here, the silicone wafer is something we are readily use, and put on there. And just kind of using your thumb or the tweezers, just rub it behind of the Scotch tape, press the crystal down to the flat surface. And then you carefully remove the Scotch tape with this bunch of the crystal. And then take a look at what is remaining onto this flat surface. As you can guess, that there are a bunch of this piece of the graphite as well as some Scotch tape glues kind of remain on the surface. But trick is if you just kind of look at this piece under the microscope and carefully, you can often see that this thin graphite crystallites are cleaved off, and there's various different colors shows up here, right? You can see that this actually has a somewhat kind of really faint color. And if you just kind of look at the various tools, so we often use this so-called the atomic force microscope. Turns out this thinnest color you can see is indeed correspond to one single carbon atom layer, what you call the graphene, sitting on this substrate. So what you see here is that this is kind of one of the amazingly easy way that you can get it. Of course, there are now many different ways you can grow the graphene crystals and different way. But initial starting of this two-dimensional study, as you see here, is a kind of such a kind of simple way. Over the past 20 years, scientists, including myself, that come up with the various ways that you can find the graphene as well as other so-called two-dimensional materials. Like the graphene, you can get the very thin materials, either grow or even just cleave down the crystal, as I showed you in the previous slide. But then you can restack them, reassemble them, and create the structures that forms with a different atomic scale of the layers. And often the different stack of the atomic scale of the layer provide a very interesting physical properties, which can be useful for some of the device application. So that's kind of some of the story I want to share today. To describe about most exciting that application based on these layered materials, I have to bring you back to the quantum mechanics. So another common topic, probably you heard about the quantum mechanics, is the so-called Schrödinger's cat. The concept of the Schrödinger cat is kind of interesting. So according to quantum mechanics, all the object, including the cat or even us, that can be described of the different quantum state superposed together. Probably one of the most extreme cases we can think about is a live cat and dead cat. Kind of two different quantum state we can superpose and make the states something like this, some half diet or half life type of this cat states. Now this is a little bit different from the zombie state, I would say, because this is quantum mechanical, the superposed state. Once you just can look at them, the cat should collapse in one of the states, so it is another zombie state. But nevertheless, this is one of the really peculiar concept of the quantum mechanics that describes so-called superposing or the entangled states. The problem of this cat, or us, as a macroscopic state, the superposed state cannot live too long, especially when there is if you just consider this the perturbation coming from the environment. However, when you have the very small objects such as atoms and molecules, often that this type of superposed state can be realized and rather robust, and you can protect this superposed state, even just kind of separate this state kind of far away and create the so-called quantum entangled state. And this superpositions and entanglement is one of the very important, the concept of the quantum mechanics, and also very important, the probe or the tool that one can use to build up some of the interesting devices. Let me just give you one quick round bit. We know that the modern electronics I just mentioned in the previously, it consists of the transistor we use as electronic switches, right? And one important part of switch is, of course, switch can be on and off. And one can just describe this one so-called the classical bit. On can be 1, off can be 0, or vice versa. But then connecting this a lot of the switches together and the electronic switches together, we can just create some of the so-called the classical logic gate operation. Basically, it's a bunch of the switches that by just kind of connecting this switch together, what you call the programming, one can just develop the instrumentation or digital circuits that do certain function. And that's basically an essential part of our computer. While that this the building up the electronic switches and make this digital computing is one of this most advanced technologies we have now, because we can now easily build billions of the transistors with very small space, then put into the computers, your phones, and act like this digital instrumentation. There's a certain limits that we can create even larger amounts of the transistor, because each transistor, when you just kind of turn and off, they start kind of dissipate the energies. And we cannot just kind of improve this one indefinitely because of this the finite limitations of the computation. There, the concept of the quantum bit provide us kind of very different perspective. So as I said, the quantum state can be superposed, and the superpositions that comes with it kind of continuous, the superposition is possible. So you can just encode a lot of more information in the quantum bit compared to the classical bits. Furthermore, we can just kind of entangle that kind of several quantum bits together and make them kind of interact each other. And in this way, that you can also just kind of operate it, this quantum informations in various very different way in the classical logic where the classical bit get operated. In this quantum logic gate, whether one can just process all this information continuously, encoding information in continuous fashions, and also that it can be completely reversible and beat this kind of a lot of the limitations of this quantum classical computation. And hence the quantum computing becomes one of the exciting new topic. They actually revolutionarily changes our concept of the computations and provide a very different scales of this capability of the computing. And that's kind of one of the really exciting topics. I remember that about the last year, Steve Govin actually gave you one of these public lectures. So probably you can find it out, a lot of exciting part of this quantum computing there. But of course, to realize this quantum computing, one needs a material platform. And in fact, scientists, engineers came along with a lot of different material platform to realize the quantum computing. And many of the material platform that based on the different type of material technologies, often that it comes with the semiconductor technology. Sometimes it comes with the dealing with the atoms and the ions in the kind of various way, or sometimes it can deal with so-called superconducting technologies or some of the other material technologies. I'm going to give you one of the view that deeply related with my research, which is the kind of superconducting qubits and the topological qubits in the kind of next few slides. But let me start with this, the idea that this is not only this scientist's dream, and now even several big the companies that invest quite of the monies to realize this quantum computing on the various different type of platform that I just mentioned. Among this platform, the one nice part is so-called the superconducting qubits. Superconductor is the materials that where the resistance becomes 0 when you just go to the low enough temperature. And because there is no dissipation of the energy when the electron moves around, when you make this superconducting ring, you can set up the currents without any just battery attached to it, and this current will not decay unless that you just do something drastic onto this superconductor, right? But then in this ring, the current can flow the one of the counterclockwise direction or the clockwise direction, and there you can just kind of build up kind of two states of this current flow. Current counterclockwise of the flow current is qubit down. Clockwise flow is a qubit up, and basically you can build up this superposer state and make this superconducting ring as the quantum bits, and that can realize a lot of interesting quantum operation. Of course, to make this quantum computer, you need kind of combine with many of these superconducting bits. And technology evolved that one can make the many bits now, about 50 bits, 100 the qubits out of the superconducting technologies. Since superconductor work in the low enough temperature, you have to just mount that into the cryostat and bring it to low temperatures and control all the superconducting qubits. So you need kind of rather more complicated technologies that rely on these RF technologies there. So it seems like that we can now build at least not billions of the qubits, but say hundreds qubits, and one can think about operating this system in an interesting way. However, there is some of the issues. One of the biggest issue here is this superconducting ring, although this acts like the qubits, has some of the imperfections in there. And since superconducting ring is larger than atom and molecule, and any environmental perturbation start kind of decoy the quantum state of the reasonably macroscopic object of this superconducting ring, and to deal with this quantum decoherence to make the one qubits. In fact, it's not. It turns out that you need many qubits come together to make this quantum error corrections to make the one physical qubits. In other words, when you try to make the 50 qubits, 100 qubits, thousands qubits, you need maybe 10,000 times, or that you may need 100 times, even 10,000 times more qubits than just kind of one the logical qubits you need for the quantum computation. As you see here, unless the one can just make the drastic changes to how to make this qubit design and how to make the qubits operating, scaling up these qubits into the scales of the classical quantum bit, the bits. There are a lot of the technological the revolution we have to create, and there comes basically this interesting part of the quantum material research comes in. I told you that one of the way that we can just go through is creating so-called topological quantum states. And you may say that, well, what is meaning of the topological quantum state, and what is meaning of this topological qubits based on that? In a sense, it is related with that create some of this the protective state which cannot be easily undo, right? Showing here is one nice schematics diagrams of the physicists use that have the strings of this states comes in. If you start kind of braid this string together and make the knots or the braiding, it can be easily undo that even if unless that we start kind of cutting out these strings, right? And often that this is kind of an easy way that we can say that we can encode some of the information in the braiding by just kind of topological sense, which means that it cannot be easily undo unless you just make the cut and the dentures through it. So in fact, the word topologies, what we can borrow from the, sorry, let me just hide. Okay, good. The word of the topology is something that we just kind of learned from the mathematics. According to mathematics, topology is the property of the object that is not depends on the detail of the geometries, but it is related with classifying this object in terms of the certain unaltered natures, what we often call this topological invariant, such as the number of the hole into the genus, So often that people say that, that topology is that the way of the we can classify that your mug cup and the donuts is the same topological object in terms of number of the genus, right? Of course, one can just play around this one and you can easily create a rather interesting so-called topologically unique or non-trivial object, something like that. This making interesting knot called the Trafford knots is one of the example. Another interesting topological object you can also do it yourself is making this so-called Mobius strip that have the strips, but attaching the strips not in the normal way, but just twist the strips and just connect them together. Call this somewhat interesting twisted form of the strip, and this is often what you call the Mobius strip. And this is a rather topological unique object. I was just going to use this one later and just hang on a little bit. Right. But again, this is mathematics. And as you see that I'm clearly not a mathematician, so I want kind of make that this mathematics is in fact not purely mathematics, but make the kind of interesting connection with the physics. And there I need kind of, again, wind the time even further, going about 150 years ago. So about 150 years ago, there is no quantum mechanics. People start to knew that, okay, so that there are charges. Benjamin Franklin's achievement is showing that indeed there's a charged object that can carry the current. So we know that there's a charged object that can carry the current. In modern world now, electron can carry the current. And this charged object near this magnet, their motions get kind of deflected. And the first person that showed that is this Edwin Hall in 1879. In the following way. So Edwin Hall just kind of theorize in the following way that if I have the conductor that sending the current and this conductor is under the magnetic field and the current is basically carried by the say some charged object electron, right? But then under the magnetic field they will deflected. Therefore, that you expect to see that there's a voltage buildup on the sideway. So that's basically an idea. Why this? Okay. One thing that important problem that he had to solve is to see that this the deflecting effect a lot. Turns out he need a really thin object to carry the currents in through them, right? So remember that it was at middle of the 19th centuries that there's no graphenes around, there's no semiconductor. The way that he come up with is basically make the gold foil really thin. Now, because gold is a precious metal, so people know how to engineer that it's a thin foil. So using this thin foil of the gold, applying the magnetic field in the normal direction of the foil, that he could successfully measure the voltage developed across this current direction, so what you call the Hall effect, right? But if you just remember that how this deflection, or so-called the Lorentz force work, that as you apply the more magnetic field, there's more of the stronger Lorentz force. Therefore, that you expect that there's more voltage developed across this current. So what Edwin Hall did is basically measuring how much voltage is induced and divided by current, that will becomes the unit of the resistance as a function of magnetic field. He found that the whole resistance or voltage across this current direction is linearly increasing with the magnetic field because the Lorentz force is linearly increasing with the magnetic field. In fact, this slope contains very important information. If you analyze this very carefully, slope contains information about how many electron charges or how many charges, how much charges you have in this the gold foil can tell you about this slope of this Hall effect, right? About 100 years later, this Hall effect come into the very interesting tweak, right? So around the 1980, about approximately 100 years later, the technology evolved and then allows us to do the following things. First of all, we can apply the very strong magnetic field. So there's a superconducting magnet coils available readily, and you can apply probably 100 times more magnetic field than what Edwin Hall could apply in the kind of 150 years ago. Furthermore, the semiconducting technology got evolved, right? Such that you can make the transistor onto silicon chips. And if you remember that when I showed this modern silicon chips, that silicon chip that can carry the switches, and switches open or on and off through this gate electrode operation, which means that when I just apply this some positive voltages, I can induce these charges, electrons charges at the surface of the silicon or interface between this gate dielectric silicon. And that is basically the channel that we can deliver the electron through this silicon pathway. The whole point here is if I just kind of put the gate electrode wide enough, the electron accumulate on the silicon surface is the electron that confined into the surface of the silicon, act like the two-dimensional system. In other words, this is a time that we know that how to effectively create the electronic system, effectively confine the two-dimensional area, right? That's a time that this person, Klaus von Kliching, just apply the magnetic field into this silicon to two-dimensional silicon and just did the Hall effect measurement again, right? And quite surprisingly, you see that Hall effect appears in here, but not in continuous way, but it's a discontinuous way. And this discontinuous is kind of rather surprising. And in fact, this is discontinuous so well established, it's kind of almost so-called quantized step appears. And out of this, basically within 5 years, again, he also got this Nobel Prize out of it, right? Now, to explain that why does such a discrete step appears in Hall effect, we have to kind of look through the physics again, the quantum physics, as you can imagine. And that was actually solved only 4 years after this, Schrödinger's, the famous Schrödinger equation. In 1930, Landau actually solving the Schrödinger equation and show following amazing things. According to Schrödinger equation, everything's basically described the wave function, and wave function has, of course, it's complex object, and it's described by the amplitude and phase. And quantum mechanics tells you that any orbit should be quantized, which means that this wave function that describes the quantized electron orbit should be quantized. And if the orbit is quantized, the phase around this orbit should be that just continuous, it should be periodic into the system. So what we are saying here is that by just applying the magnetic field and quantized orbit, somehow we should just make that this phase or winding of this wave function should be quantized, right? And now that's basically interesting the topological concept, because we are talking about electron is confined into the 2 dimensions. And if I just draw these circles around this, they make the quantized orbits. And if I just ask that to make the complete these orbits without any cut, how we can do that? We can just winding once or winding twice. And this kind of so-called winding number of the wave function phase around this orbit becomes kind of something that describes the discreteness and something to do with this kind of topology we are talking about. Turns out precisely this orbit that I described, the quantum step I just mentioned, shows that this interesting the integer number associated, in a sense that first step, if I call this as first step, and second step is half of the height of the first step. Third step is 1/3 of this the height of the first step, and so on, right? Turns out all of this the discrete numbers, integer number I just kind of put up there, is precisely related winding number of these orbits I mentioned that describe this quantum state under the magnetic field. So what you see here is a very nice example that how this concept of the topology, in this particular case, a winding number, is really related with the experimental observable that you can just kind of find out in effectively low-dimensional system. Because of the protections or the nature of the topological protection is rather robust. In fact, this quantum Hall effect can appear even with rather rugged condition. Take those kind of wafers showing this quantum Hall effect. I just kind of carve it down and make this one and try to place some of the disorder, but nevertheless, this type of sample, that quite ugly sample, beautifully show those kind of this nice the quantum plateaus that I just mentioned, and that's because it is deeply related with the topological nature of the wave function innately there, right? So you see that this kind of strength of the topology is there. Why this is useful and interesting? Think about that. I just kind of have this quantum system, apply the magnetic field, right? The orbits inside of the sample is quantized, but nevertheless, orbits at the edges start kind of flowing through that the bouncing off, make those kind of this the information path, the current pathway, with where the current cannot be easily just kind of decays out. So unlike the superconductor, in this cases, the current flow is only one direction, but very similar like to superconductor. Once current is set in here, it does not decay because of this topological protection, right? Immediately we can think about those kind of straight pathway in the following way. In typical metal, that where we have the electrons crowdedly located inside of the any materials, there is not only electron, there are impurities. There also in finite temperature, there are the lattice vibration, also happily scatter of the electron, right? It's a situation that when electron flow in semiconductor, typical metal, is something like this. You're just kind of crossing through this very crowd, the streets in the markets. All sort of different type of events and scattering events make this electron flows are really kind of slow because it's kind of bump off the many different things. We know how to make the traffic. It's kind of going really efficient way on the in this way. It's basically we can just make the lanes of the road and make this kind of only one direction is moving through the kind of specific pathway, and that's precisely I just showed you how the quantum state can deal with, right? Basically, you can set the electrons into the certain pathway in the edge state, and without scattering, one can flow the one direction, make this kind of flow extremely efficient, right? Okay, so sounds like that this is kind of one way we can obviously apply some of the interesting applications, but there is one catch that to realize the quantum effect, we need a very strong magnetic field. To get this very strong magnetic field, we have to cool down sample very low temperature and big magnets needed, which is kind of interesting things. So we can study the physics, but not easy things. So we can realize application based on those kind of materials. For that, we have the yet another tweak. And that brings us yet another interesting quantum mechanics. And I will tell you another interesting aspect of quantum mechanics and topological object. That's related with the electron spin. So electron is an interesting object. It carries its own spin. If I just think about electron as ball, which is kind of, I know that Dean probably doesn't like that the concept as a theorist, but let's classically think about the electron as ball. It's a charged ball, and you can just spin this the charged ball. And because of this, the electrons, if the charged object kind of rotated, it started to develop so-called magnetic moments, right? So it becomes a small magnet, which means they have the directions up and down in certain directions, right? However, electron is also quantum mechanical object, and this is so tiny, I cannot make this classical ball. Turns out this electron spins, or the magnetic moment, has a very interesting properties. Saying that, although this is magnetic moments that can direct in any direction, turns out quantum mechanically, it can be only described by the spin up and down. That's a kind of weird statement. Even if spin x, the magnetic moment is, this arrow is pointing x direction, somehow I should be able to represent in quantum mechanically only is up and down spins together. Turns out this two componentness of the electron spin provide a very unique property of the electron spins. It's the following way. If I have the electron, turn around the electron 360 degrees, if I'm naively thinking it should come back, it is on. But turns out quantum mechanics tells you that when electron turns out 360 degrees, it doesn't come back its own, but it should come back with the sign differences. Okay, so let me just say right. And only when it turn around twice, say make the 720-degree rotation, it come back its own, right? And this property is kind of unique, but has a very interesting analogy in mathematics. Think about the Mobius strips. And I starting from the one Mobius strips, and let's say pointing up, right? And just kind of follow this Mobius strip and come back 360 degrees. You'll find out the point that I started with is coming through the bottom of the surface and pointing down, right? It's only when you just kind of rotate that another turns that you come back to the original position you just come back started with. So interesting part of this Mobius strip is in some sense you have to turn twice to this along the strips to come back to its original position, which actually very analogous to what I just mentioned about the electron spin. And from this analogy, you can see that there is an interesting the connection between that electron spins with the topology I just kind of mentioned there, right? Often this is kind of mathematician called the interesting property of the SU2 spin object, right? Again, this looks like the mathematics, but can I just look at the experimental observable? There are many experimental observable, but in fact, you can find this interesting observable in graphene. I told you in the graphene, there's carbon atoms made of the carbon atoms. But if you're staring the graphene carefully, there are two different carbon atoms, like the carbon atom sitting in here, carbon atom sitting in there. Let me just color it. These carbon atoms sitting as a kind of network in this way. This the blue carbon atom sitting in the network in the other way. Turns out, quantum mechanically, describing electrons in graphene, I have to use this the fact that there are two different carbon atoms in this repeating units, and I need kind of two component of the wave function to describe this one. And this two component is basically exactly analogous that two components of the spinors I just mentioned before, and therefore, like the very similar statement I made, electron that traveling into the graphene lattice has a very similar properties. When it's circulating around, it should travel twice to come back its own wave function phase. And if you just travel only 1 ton, it actually effectively kind of give you only half ton of the rotation, right? So what is the implication? Implication is once you apply the magnetic field into graphene, electron confined in graphene like the two-dimensional system, and then you asked what you will see here is that, of course, as a two-dimensional system, it actually provide some of the quantum effect. But interesting part is when you just look at this quantum effect is not appearing with this old integer number I just mentioned, 1, 2, 3, 4. It goes like the 2, 6, and 10. Interesting sequences, right? So step appears not in the regular step, but 2, 6, 10, and 14. Now, question, what is the next numbers that you expect to see after 14? Well, you may guess it's 18, right? So what is a general rule? So if you just write the general rule is basically that is a 4 times of a half integer, right? And what you make the difference is basically the presence of a half integer. That's basically related with the fact that indeed graphene spin or graphene electron, you have to make the 2 tons to come back its own. If you make the only 1 ton, it's effectively half ton, and that's basically origin of this half integer. And again, this is a nice example that how the topological the consideration becomes quite important to understand physical observable. In fact, this is the interesting part, and showing the topologicalness of the graphene. Turns out, based on this one, there are several important contributions from these two theorists that David Dowless and Duncan Haldane made this important contribution. Extend this idea further and show that, in fact, you can just kind of build up this topology into the materials such a way that, unlike the graphene or two-dimensional electron system, to see this one, you don't necessarily need even just look at the under the magnetic field. Following through the seminar proposals, in past probably 15 years or so, the scientists found that materials that you can just build up this topological edge state, or this I will call this the information highway without magnetic field. And there's kind of now the material has been developed that one can come up with these materials that created those kind of the topological state without evoke of this magnetic field based on these topologies. Right. Among these many materials, I just go showing you again here. Some of this two-dimensional material is a kind of good candidate. You can just realize that this topological quantum state, which might be applicable to some of the applications, right? So as you see here, that there are many different 2D materials, you can stack them together to form these heterostructures and build up the interesting material properties. If you just put kind of different type of materials together, you can build up the rather interesting functional system, as you just kind of analogically shown in this Lego model, right? But there is one thing that I just missed it out. That's kind of probably the last subject within the next 10 minutes before I just close down this talk. one thing, that difference between this stacking of the material, especially this layered material, the what you call the Van der Waals materials, with this Lego system. In this Lego material, as you just play around the Lego, that when you stack them together, you have to really register these atoms together and lock them together, right? If you just misplace it, basically you cannot assemble these Lego pieces. However, that's not the case for these two-dimensional materials. 2D materials, because of there's a less interaction between the layer, when you just kind of put them together, we can put them together with the various different material choices, but more importantly, different the twist angle. And often this kind of twisted kind of stacking is what you call this Moire engineering. The reason that you call the Moire engineering is following, that if you just look at this screen, as you just kind of twisted these materials together, there are rather complicated patterns appears, right? Unlike this atomic length scale of this periodicity, there is a kind of even larger quasi-periodicity appears in the system, which is what you call the Moire periodicity, right? And this Moire periodicity is kind of rather interesting things. And also you can see that this is kind of the mathematical object, because you can just kind of play that very similar role. And I don't know whether this type of the toy is still popular. That when I was growing up, I think this toy called the spirograph is one thing that you can just play around. And this is something like this, right? There's the gears out there and the small gears inside, and you just put the pencils in there and rotate this one, and you can create the kind of rather interesting pattern, rather complicated pattern in the kind of interesting way. If you just look at this pattern carefully, however, this is a periodic pattern. The periodicity is related with how many gear tooth you have on the inner circle versus how many gear tooth in the outer circle. And periodicity is related with basically this the ratio, the relative ratio between P of Q of the different type of this tooth length, right? But you can ask following: what if that this the P of the Q is not just the rational number, but if I just put this irrational, right? Then it becomes quickly this non-periodic structures, but contains a lot of width of this type of interesting things in there, right? And that's basically related with the topic that I want to mention about the Moire, right? In fact, that topic that I just mentioned is one of the important topics of this book that written by the Douglas Hofstadter. I know that this is a relatively old book, but it is the Pulitzer, the winning the book, and maybe some of you already read about this book. In this book, Douglas Hofstadter actually connected a very interesting concept like the Gödel, Esch, and Bach. Gödel is mathematicians, is a very important, they come up with a very important theorem in the mathematics, so-called the incompleteness theorem, tells you that the consistent axiomatic formulations must have some of the undecided propositions, which make the kind of almost the complete mathematical structure is kind of impossible by just kind of showing this one. Painting of the Escher is also somebody, many of you already saw that, already kind of describes something like the somewhat interesting distort space together, right? Come up with an interesting way. And let's see, okay. Point option to hide. Okay, I don't know how to turn it off. This one. Sorry, let me see. I can. Let's reshare.
It's okay.
Yeah. Okay. Good. All right, doesn't work. That's okay. So I was about kind of the background, the music is actually Bach's the endless canon, actually also in this book, kind of merging together with the concept of the basically some interesting the infinite loop with almost periodic structures, which actually ties back to this something that I mentioned, right? But let's know about this book, by the way, is if you just look at this book carefully, there is the interesting diagram, what called, okay, here we go. But anyway, interesting diagram is shown, which is so-called what he called the G-plot, right? And in the modern languages, it's kind of the fractal. It has kind of something is repeating in there, not completely periodic, but something is repeating. But you may ask that why it comes around this kind of interesting diagram. You know that the Douglas Hofstadter is also a physicist. He wrote the kind of important papers about this, the solution of the Helmholtz equations, which is precisely the problem I just mentioned before. When there's a two competing periodicities, one generated by the electric field modulation, like the lattice structures, one generated by the magnetic field that can make the lambda orbits, how they actually compete each other, and that's kind of incarnated in this Helmholtz equation. Hofstadter actually solved this one by numerically using this old computer available back then. And that's kind of basically he comes around this spectrum of those states and what he called the G-plot and put it in his paper. Basically, this G-plot is a good example showing that how that the quantum factor appears into the system. In fact, this type of the spectrum can be studied into the Moiré system. If you just put the graphene together on the graphene or graphene on the top of the boron nitride, create the atomic scale of Moiré, and measuring quantum effect, and you will see the quantum effect becomes fractalized, which means there's kind of the spectrum that follow through that so-called this Hofstadter G spectrum comes around. And Hofstadter originally didn't call that as a butterfly, and the later people that this G plot looked like the butterfly, and there comes that the word of the butterfly comes around, right? The whole point here is basically this Moiré engineering now allows us that they created those kind of nearly incommensurate quasi-crystalline structures that engineerably created. And those kind of states start to show amazing properties. For example, the graphene becomes never superconductor before. But when you just put this graphene together with the right angle, that few years ago, that the group led by the Pablo Harriero beautifully demonstrated that superconductor sets in with specially engineered these Moiré structures. And following work of the many people show that by just changing this Moiré twisting angle, you can also obtain a lot of interesting properties out of a system created. This field is much richer. So the expectation is this Flatland engineering, that Moiré engineering of the 2D materials, start to show that the a lot of possibility. One can build up the interesting the properties of the electronic states, including topological states. And this is probably the one of the hope that we have. Using this type of the topological electronic natures or correlated electronic natures on the top, that one can build up the useful electronic system that can be useful for the quantum application. All right, that's kind of end of my talk. I want to end my talk that indeed the kind of, okay, the advertising, there's even Flatland 2 movies available, right? Like these movies get involved. The scientists also kind of keep pushing around this our boundary of the materials, come up with interesting application. Right. I want to end with my talk with acknowledging my group that just kind of bring all this kind of subject together to interesting presentations, hopefully, and then pushing front of this our research together. Thank you.
Thank you so much, Philip. That was a beautiful talk where you brought in lots of really interesting physics and explained in a very clear, exciting way. Thank you so much. Those of you who have questions, go ahead, put your questions into the question and answer or the chat, and I will read them. Otherwise, maybe I'll start off with a question. So you mentioned that they used the Scotch tape to see the graphene, to collect the graphene layers before. My question is, you said there are new techniques, more advanced techniques now. What techniques are being used these days?
Yeah. So interesting enough, in the lab, still the Scotch tape is one of the techniques we are using. Because a part of the reason is that as a physicist, we care about the quality of the sample. And oddly enough, that the material comes with higher quality with a single crystal. So the best way that still you can get the highest quality material is often still using Scotch tape. You cleaved up these thin materials down onto substrate. And of course, from there on, it's a little bit more high tech. However, for scaling up applications, the people know how to grow these materials in the larger scale. For example, that there's a chemical vapor deposition technique. One can use this copper or some metal substrate, blow in the hot gases, and one layer of the materials grow and it just end there. And this is often the technique one can use to grow even meter scale of the sample.
Mm-hmm.
There are also other methods like the metal organic chemical vaporization technique, MOCVD, that allow to grow the electronic grade material onto the wafer scale. So there are quite of these different techniques now people use outside of scarce tape. But oddly enough, the many physics lab, especially that somebody want to work on the do not mind to work on the very small scale samples, say micron size of sample. Scotch tape technique is still being used widely.
Mm-hmm. Okay. Um, Another question I have, so as you try to engineer new, interesting 2D materials, what sort of intuitively makes a given material interesting, or how do you know whether it will be interesting or not? Is it the dispersion relation? Is it some sort of number of atoms per unit cell? What are sort of the magic features that are important?
Yeah, that's a very good question. I think, well, I wish I know that whether general rule is there. Initially, I think the discovery graphene is a rather, I would say accidental. I think that we knew that some of the part, but it was not really theoretically driven and designed. But the after many years that we developed a little bit more intuitions. So, for example, that topological unique structure is related with, as you said, the dispersion relation, especially where that so-called the Dirac cone is appearing somewhere, right? And often, what is the condition we can create those kind of Dirac cones into the band structure? I think these are some of these intuitions that we start to learn from studying of the many different materials. Also, there are many different type of materials that we can study and stack them together. The phase space of our study becomes really wide. Now, not to mention about if you think about if I stack this material with various different angle, you may get the different properties. Then you have to think about what angle we have to study, right? So once you get into such a wide phase space, we have to explore. It becomes quite evident that we need a really close connection with the theorist, especially theorists who can just do this band calculations, and now even just tied with the machine learning, then screen out this large phase space and just tell the experimentalist what is interesting system you want to look for and what type of the stacking and stacking angle and those kind of the information.
Okay, great. So there is a question from Sukyung Kim. Thanks for a wonderful talk. When I try to put a protective film on my cell phone, it never goes perfectly but forms a bunch of air bubbles.
Yeah.
How do physicists go around this problem when stacking layers?
Oh yeah, that is very good question. In fact, that's oddly enough, that's precisely the problem we have in our labs as well. So I think not only cell phone cell phone part, but the when we stack this material together, right? That often that you just kind of trap the air bubbles in between them. So when you just kind of look at all the stacks, often you see that there are bubbles here and there, and precisely that put the thin film of the scarce tape. So the way that we can get around that, of course, is that you just do it in the vacuum. So you just kind of put into everything in CHV conditions, and there is no airs, so such that even if you just kind of land in some wrong way, you don't trap the air bubbles in there. So that's kind of one way. The other way is probably also you can learn from your own experience. That one way you can just do that is ironing. Using the a little bit hot substrate and just kind of try to loosen the films a little bit and push away this bubble. And often that is also what we are using in our lab. So what you just do experience and the empirical experience is something exactly what you are doing in the lab as well.
Very good. There's a question from Dasuni Rathnawira. Hi, thank you for the interesting talk. How do you precisely control the angle of each graphene layer practically in order to twist them and stack them together?
That's also a very good question. So the way that right now is being done is again, I told you that we just clip down the crystal on the bottom of the surface, right? So that is the fact that that is a single crystal. So we know that that part of the crystal orientation. So we just stack them by just picking up this crystal only halfway. So we just cut this crystal and pick up only half, and then before you stack together, you just kind of rotate it with the some angle and just put them together. In such a way, you can control the angle rather precisely, down to 0.1 degree or even less.
Okay, that's very clever. Okay, let's take one last question. There's a question: when the magic angle graphene becomes superconducting, do you know the path of the electrons, or do the electrons travel uniformly from one edge to another?
That's a more professional question. At this point, let me just take that question's following way. Do I know that whether the superconductivity magic angle graphene is a topological superconductivity or not? If I just convert that questions in that way, the answer is not yet. There are a lot of the study has been done in the magic angle graphene as well as similar system for the superconductivity. There are some tantalizing evidence, experimental evidence that piles up that pointing out that superconductivity may be unconventional, which means that including the topological superconductivity, but we don't yet have this really smoking gun experimental evidence it's pointing out there. And one way that indeed study about this topological nature is study that whether the the supercurrent, well, it's actually not the supercurrent, whether there is this the charge neutral edge mode forms in the edge of this superconductor. That is another one of the smoking gun evidence whether this is topological or not. And many people, including us, are trying to just kind of see that the case. There is no experimental verdicts out there.
Okay, well, thank you very much. Let me stop